And we are back for single phase motors part 3. While you're away, I figured out how to do a neat little thing. I just want to show you. Check this out. I can go from this view to this one. You can just see me. Or if I click this button, just the presentation. And then back to both. Look at that. Amazing. I haven't figured out what I wanted to use that for, but the fact that I can do that fills me with joy. I just wanted to share that with everyone. Stay tuned for future videos where I use that little transition effect. That'll be neat, wouldn't it? Alright, let's carry on. So we're moving on to permanently split capacitor motor. Permanently split capacitor motor. So we just talked about capacitor-start motor. That's a permanently split capacitor motor. In this motor, the capacitor remains in series with the auxiliary winding permanently. This motor has the advantages of simplicity, reliability, high efficiency, relatively silent running. Because the capacitor is permanently connected and must therefore be capable of continuous service in an AC circuit, it has a solid dielectric capacitor. The electrolytic capacitor is not used because it's short time rated, so that we can't continuously use the electrolytic capacitor. It's only for short bursts. Both the windings are identical and therefore have the same resistance and number of turns. The circuit diagram for the motor is shown. Here it is here. So we've got phase coming in and main winding back to neutral, just like we've had on all of our other ones. And then our starting circuit has the capacitor auxiliary winding. What's the difference? Well, there's no centrifugal switch on this one, right? So the capacitor and auxiliary run winding are in, or auxiliary winding or start winding are in all the time. We call this one, we're going to call it an auxiliary winding now, not a start winding, because it's not only limited to starting. It's going to be in that circuit all the time. So how does this work? Well, then we've got that capacitor providing the phase shift to the auxiliary winding, so that puts the auxiliary winding and main winding out of phase with each other, which creates that magnetic, rotating magnetic field effect. And again, here we have it here. What does that say? Is that 80 degrees? Let's have a look at that a little bit bigger. 80 degrees. So then your auxiliary and your main windings are about 80 degrees phase shifted from each other, and then that's going to operate permanently like that. It means that we need to beef up our auxiliary winding a little bit, as it says there. With the capacitor start, then our start winding it's only going to be in for a brief period. It's pretty fast. In most cases, it's like a couple of seconds, if that, even less than that. So it doesn't need to be rated for continuous operation, where this one it does. So the auxiliary winding will need to be a bit bigger, able to withstand a little bit more or longer running time than it did before. Because both windings remain in the circuit permanently, the need for a centrifugal switch is eliminated, along with the potential maintenance problems associated with it. All that means is that, you know, a moving part inside the motor means that it's just a moving part that can go wrong. It's something that can break. If we don't have it, then it can't break. This simplifies the circuit and makes the motor more reliable. The capacitor is sized to provide a more constant strength stator magnetic field while running on load. That is, with the two windings permanently in the circuit, the stator magnetic field produced is similar to that of a polyphase motor, resulting in a smoother running motor that does not exhibit the noise or characteristic pulsating hum of the standard and cap-start motors. So we've just got that nice rotating magnetic field all the time. If we had 90 degrees or around about 90 degrees phase shift, then that would give us basically a perfect two-pole rotating magnetic field, if you think about it like that. It won't quite be as good as a three-phase, but it'd be like a two-phase basically. It's like a two-phase rotating magnetic field. If we were to get 90 degrees phase shift, which we're probably not, but we can probably get close to that. Rotation reversal. So the motor reversal is more easily achieved than with the cap-start motor, and a reversing switch can be connected to enable the capacitor to be shifted from one winding to the other, as shown. This effectively changes the direction of rotation of the stator field and in turn the direction of the rotor by dictating which winding will have the leading phase angle. So let's have a look at that there. So we have the capacitor. So in this case, current runs through here, that runs through the capacitor, and then through this winding here, back to neutral. Through the capacitor, through this winding, back to neutral. If we switch it over here, then the reversing switch, that one becomes in the circuit all the time, just goes through there to neutral. This one goes through the capacitor, through there. So basically, just by that little changeover switch there, we can change which winding has the capacitor with it. And like we said earlier, because both of those windings are going to be in the circuit all the time, then the auxiliary winding is no longer like a little start winding. It's basically the same as the run winding. So we make them both the same, and then we have a little changeover switch that decides which winding will have the capacitor in series with it, and then that way it's going to change which one is leading and which one's lagging. So it's going to change the direction of that rotating magnetic field. So the speed controls, not speed control, the reversal was easy. The size of the phase angle between the respective winding currents depends on the actual speed of the motor and will vary as the motor speeds up or slows down. With this in mind, the capacitor size is selected to produce optimum performance and torque at full running speed. This is quite different from the cap-start motor, where the capacitor is chosen so that high torque is produced at the start when the motor revolutions are slowly building up to speed. What does that mean? So that means that we're going to then have to, or we'll have lower starting torque, right? Because we're with the cap-start and the centrifugal switch, we can finely tune that start winding and the capacitor to deliver the maximum torque at that low speed, at the startup speed. Whereas because this one's going to be running all the time, then we're not going to. We need to have it so our best performance will be at full speed. So we're going to go back to having low start torque. So we're limited then in the type of things we can use it for, because we're back to stuff where not only low starting torque is required, or we don't require high starting torque. Fans produce the speed torque characteristics like this, and therefore make ideal loads for these types of motors. Extract and intake fans, blowers, and the like are typical applications for these motors. So they don't need high startup torque. Why don't they need high startup torque? Well, if you think about a fan, the load on it is the air that it's moving, so it moves more air at higher speeds, therefore the load is higher at the faster it's turning. So when it's starting up, there's not much load on it because it's not pushing much air. As it gets faster, then the load increases. So so that means it doesn't need a high starting torque. It needs more torque at full speed as opposed to low speed. And then we have a cap-start, cap-run motor. This motor combines the favourable characteristics of the permanently split capacitor motor with the capacitor-start motor by using a centrifugal switch to cut out one of the two capacitors wired in series with the auxiliary winding. And here we have it here. So if you got rid of the this part of the circuit here, the centrifugal switch and starting capacitor, then you just have the permanently split motor. If you got rid of the running capacitor here, then you just have the cap-start motor. So this is actually both. We've got basically got a cap-start circuit in parallel with a cap-run circuit, and then the centrifugal switch either brings that capacitor in, meaning we use for starting, we use the starting cap, and then drops it out. So we just have the running capacitor, and then we have the advantages of that full load torque and smoother running that we get from the what was the other one called? Permanently split capacitor. I thought it was. I just needed to check because these names are so similar. If I get the wrong one, I'm going to confuse people. So that we get the advantage of the higher running torque or higher operating torque and smoother, better rotating magnetic field of the permanently split capacitor motor. The combined capacitance of the parallel connected capacitors, one electrolytic with a high capacitance for starting and another will be a solid dielectric with a low capacitance for running, splits the phase angle between winding currents to nearly 90 degrees at start. This produces a high starting torque equal to that of a cap-start motor of the same power rating. The run capacitor that remains in the circuit after the centrifugal switch is operated maintains the phase angle and effectively converts the motor into a permanently split capacitor motor. So it has all the favourable characteristics of smoother, quieter running and improved run torque associated with it. Motor reversal is achieved in the same manner as the cap-start motor. That is, you need to swap the connections on either the auxiliary or the main winding, but not both. Applications. This motor is suited to the woodworking machinery, for example, saw benches and wood lathes, also floor polishers and refrigeration units. Any situation that requires a high starting and a high running torque. Yeah. Floor polishers are great. I used to fix floor polishers when I was in the army. Great for understanding this sort of stuff. I remember when I was posted to Wairuru, because you have the floor polishers when you're in basic training. I think I've talked to you guys about that before. I mentioned floor polishers. And so the recruits would break them all the time. So they would send them down to us and we would fix them up. And I learned a lot about centrifugal switches and capacitors and basically everything I know about single phase motors. Everything we're talking about was I learned from working on floor polishers. Great fun pieces of kit. Hate polishing floors though. External start winding relays. Right, okay. If the sparking caused by the operation of the centrifugal switch in a split phase or cap start motor is likely to be dangerous, an external relay is used. This is particularly useful for motors that have their windings submersed in oil, as in the case of some refrigeration compressors. By being situated outside the motor, the external relay allows the motor to operate in this environment. Another reason for a designer to choose an external relay is to make a more compact motor. So what that means is that we would still have the two different windings inside the switch, inside the motor rather. But we don't have that centrifugal switch, because that centrifugal switch is going to cause sparking, obviously, by its very nature. It's going to be opening and closing under high current, and then it will cause a bit of sparking there. So if we don't want that sparking, then we could use an external relay. What would be the advantages, disadvantages there? Obviously, the advantages are that we don't have that sparking. The disadvantage would be that the centrifugal switch inherently has a specific motor speed tied to it. So when it reaches a certain motor speed, then the centrifugal switch opens. If you're using an external relay, you don't have that inherent or native connection, if you like. It would have to be on a timer, or you'd have to have a separate motor speed sensor that then switches the start winding out when it reaches a certain speed. You can see that could then start getting quite complicated, right? Probably a timer would be the best one. When you turn power on, then that relay will switch off at a specific amount of time, like 0.3 seconds or whatever you think that's going to time it's going to take to get up to speed. Current relay. Current operated relay is used to open the start winding of a split phase motor. Oh, here we go. Okay, so this is how we do it. When the supply is switched on, the high starting current drawn by the run winding causes the relay to pull in and close the start winding contacts. The motor starts and the current through the relay begins to fall. At about 0.75 of full load speed, the current through the relay is so low that it could no longer hold the relay in. The relay opens, the start winding is disconnected, and the motor runs on the run winding only. Newer solid state relays send the start current electronically and use electronics to disconnect the start winding. Okay, so it's not an external speed and it's not a timer that I just said it might be. It's this current relay. So it's based on the amount of current that's running through the run winding. And as it draws more current on this, when we first turn it on, like actually if this is open and we first turn it on, then we'll have a really high current, because it basically short circuiting that run winding. The motor's not turning because there's no spark torque created. So that very high current will immediately pull the coil in, which closes the relay and brings our start winding in, and then we go. And then the current is going to slowly decrease through the run winding, because we're no longer pulling that high starting current, and therefore this will open. A potential relay. Potential or voltage operated relays are employed with capacitor-start and capacitor-start, capacitor-run motors. potential relay differs from the current relay in that the coil is wound with many turns of small wire and connected in parallel with the start winding rather than in series with the run winding. The relay contacts are in series with the start capacitor and are closed when the motor is not running. When the motor is energized, both the start and run windings are in the circuit. As the motor starts to come up to speed, the voltage in the start winding increases to about 1.5 times the line voltage because the capacitance of the capacitor and inductance of the start winding are approaching resonance. Don't worry about what that means. You'll learn about that one day. Just believe it. This high voltage across the start winding produces a relatively high current flow through the relay coil at about 75% of full speed. The current is high enough to cause the armature to pull in and open the starting contacts. The opening of the relay contacts of a capacitor-start motor disconnects the start winding and start capacitor from the supply. In the capacitor-start capacitor-run motor, only the starting capacitor is disconnected. Obviously, the running capacitor remains in. In both types of motor, the run winding induces the hold-in voltage to the start winding by transformer action after the starting contacts have opened. Although the induced current is lower than the current during run-up, it is still high enough to hold the relay contacts open until the motor is switched off. Simple enough. Shaded pole induction motor. Give me a second. Okay, let's carry on with shaded pole induction motor. We'll get through this one and then I'll take a break and we'll come back with part 4. While I'm thinking about it, third digit of your code for this test is it's a 1. Third digit is a 1. Okay, so a shaded pole induction motor. The low starting torque and very poor efficiency of this motor make it unsuitable for anything other than small power applications. For this reason, it usually comes manufactured with a typical output power rating of around 40 watts. So we're talking shaded pole motors are going to be quite small. The attractive feature of this motor is the simplicity and robust nature of its construction. No centrifugal switches, capacitors, commutators, or special start windings are needed to produce a starting torque. That means it's a very cheap motor to manufacture. This motor relies instead on the shaded pole effect to produce just enough torque to start and maintain the rotation of the rotor. Let's have a look. And here we have it. This is a typical shaded pole motor. Pretty neat. Again, very small. You find them in like cheap little fans and stuff like that where you'll find shaded pole motors. There's very few moving parts. Only the rotor is the only moving part. We don't have all the, we don't have capacitors. We don't have centrifugal switches. None of that stuff. Makes it more simple. Okay, so this figure shows the simple 2-pole shaded motor with a squirrel cage rotor mounted between the poles. Each pole has a short-circuited coil of 1 turn, called a shading ring, placed around about 1/3 of the pole. The shading rings, which are fitted into slots in the stator poles, are made of solid copper wire or strip. To increase the starting torque, some motors have 2 or even 3 shading rings fitted to each pole. Okay, I will say at this point, again, go back if you haven't. Go and watch the videos, the other videos on Canvas. There's a really good shaded pole video, or couple of shaded pole videos, which will explain this way better than I will. I will give it a brief once over, but how this works, you go and watch the other videos in Canvas that will tell you how this works. Okay, so we have our main winding here. That is putting a magnetic field into my core. This is the core. So the magnetic field will flow through the core from north to south. Let's say this is north, this is south. So it's going to flow through here. My rotor will be in that magnetic field, and therefore it's going to want to turn. I've got north on this side, south on this side. Well, actually it won't want to turn initially because I've just got a north and a south. Now what does this do? This here, I'm just going to say it's going to interrupt the magnetic field. It's going to distort that magnetic field. So instead of having a clean north and a clean south, there's a small distortion produced at the shading rings. It's just a copper ring. So it distorts the magnetic field, and it makes the magnetic field a little bit out of phase with the rest of the magnetic field. So then it's creating that small phase shift that we saw before. It's not actually creating a phase shift because the current in the winding doesn't change. The current in the winding is fixed. What it does is it has the same effect, but it does it by altering the magnetic field directly rather than altering the current flow, which is creating the magnetic field. So it's altering the magnetic field in this in the pole there. and therefore it makes that magnetic field either lead or lag, and does the same over here. So we're just creating a small rotating effect that will help the motor turn. Like I said earlier, the disadvantage of that you can probably see, but it's not going to have much of an effect. It's going to be pretty hopeless at producing much torque. The advantage is it's cheap and easy to manufacture. Like I said, there's no moving parts in it other than the rotor. So that's why I would use it on small applications, small cheap stuff. Okay, so the copper shading ring works as a short-circuited turn on a transformer core. The main field flux induces alternating current in the shading ring. It then produces its own magnetic flux, which opposes any change in the main flux. So the magnetic flux in the ring lags the main flux, right? So that ring there is attached as a coil, is attached to a supply. So that's a small magnetic field created in there, and that's pushing back against the main magnetic field. In effect, there is a magnetic flux continually shifting from the main pole to the shaded pole. This shifting magnetic pole across the pole face forms part of a rotating magnetic field. So then we get the effect of a rotating magnetic field. Thus, the cage rotor rotates in the same way as the split phase motor. Starting torque has been produced by splitting the phase, as the single phase induction motor does. The shaded pole motor has a low starting torque, about 35% of full torque. Its slip is high, about 15%, and efficiency is very low, lying in the range of about 8 to 15%. To vary the speed, you can add a resistor in series with the motor. A resistor bypass switch provides two-piece speed control, so resistor in, resistor out. The reverse direction can be attained by turning the whole motor around, but this does not reverse the direction of motor rotation. Basically, the shaded pole is electrically non-reversible, so you can't reverse the rotation of it. You could turn the motor over, and then the motor's turning in the same direction. You're just looking at it from the opposite way. Because those shaded poles are fixed, theoretically, if you switch the shaded poles to the other side of the pole, you switch the shading rings to the other side, that would reverse the direction. But you can't do that while it's running. You would have to, I think you can see what I mean. The very low starting torque of this motor limits its use, but it's commonly found in small appliances. They're used to drive small fans, animated models, juice extractors, coffee grinders, some early tape decks, and record player turntables. So, not much really. Fans, small fans, probably the main place that you'll find it. Okay, let us stop here. That is the end of part 3, and we will be back shortly for part 4.